Okay, now we know different types of concentration, I mean the main types of concentration that we use in future lectures. And as I said, we have three mathematical equations of equivalence law. So once again, we know that for different chemical reactions, all chemical substances, all components in these reactions, both reactants and products, have the same number of equivalents. But as we already know, normal concentration normality is the numbers of equivalents in 1 liter of all solution. But of course, in the practice, we not always use just 1 liter of all solution. We can use 3 liter, we can use 100 milliliters and so on. So how we can calculate in this case numbers of equivalents in exact solution which we use in experiment? Obviously, we can multiply normal concentration on volume of this solution. And in this case, we can rewrite law of equivalence for solutions. So, product between numbers between normal concentration for substance A equal and volume of this substance, of this solution, I mean, is the same as a product between normal concentration for solution B and volume of solution B. Of course, we can combine it, we can mix in this situation different mathematical equations for law of equivalence. For example, we know that one substance, a pure substance, for example, I don't know, pure metal, and this metal reacts with a solution of acid. Of course, for pure metal, for example, we can use pure masses. I mean, we can calculate numbers of equivalents, like a ratio between mass of this metal and equivalent mass. But for solution, we can use concentration, normal concentration, and volume if you know it. If you don't know, but we know mass of this substance in solution, pure substance which react with metal, we also can use masses. So it depends on the situation, depends on exact task, and all these examples we will see. Let's see some examples of exercise where we use law of equivalence. First task. Combustion reaction of metal produce one equivalent of oxide, and we need to calculate mass of metal required for this reaction. So, we have one equivalent of metal oxide, and we know that equivalent mass of this oxide equal 40 grams. Our task to calculate mass of metal participating in this reaction. According to law of equivalence, numbers of equivalents for all components in reactions equal. So, equivalents, numbers of equivalents for metal equal to numbers of equivalents for oxide. In this situation, we can say that reacts one equivalent of metal and one equivalent of oxygen, because we have combustion reaction. Equivalent mass for oxygen, O2, we already know it equals 8 grams. And in this situation, according to Lomonossov's law, we can calculate equivalent mass of metal. It will be difference between equivalent mass for oxide and equivalent mass for oxygen. So, 40 grams minus 8 grams equal 32 grams. So in this situation, in this reaction, we need 32 grams to produce just one equivalent of all oxide. In next act we have almost the same situation, but now we know equivalent mass of metal, and we need to calculate the percentage of oxides produced in this reaction. Well, equivalent mass of metal equal 9 grams. Let's consider that in reaction reacts just one equivalent of all of this metal. In this situation, numbers of equivalents for metal and for oxide, as well for oxygen, equal 1 mole equivalent. So we can calculate equivalent mass for oxide like a sum of mass for metal and equivalent mass for oxygen. Equivalent mass for metal we know is given 9 grams. Equivalent mass for oxygen we know as well, 8 grams. And now we can say that equivalent mass for all oxide, 17 grams. To calculate percentage of this substance, complicated substance, we need to remind what does it mean mass fraction. Mass fraction, it's a mass of this element in the mass of all oxide and multiplied 100%. So in our situation, mass of oxygen equal 8, mass of metal 17 multiplied 100, and in this situation, mass fraction for oxygen exactly 47%. The same situation with metal, mass of metal over mass of all oxide multiplied 100%, 9 grams over 17 grams multiplied 100, and it gives us 53%. In this task, we have as well combustion reaction, but now we know that valency of metal equal to, and mass of metal 2 grams, and it produces 3.315 grams of oxide. And our task to calculate equivalent mass for metal and its atomic mass. So we need to know which metal we have in our reaction. According to law of equivalence, the second mathematical equation, we have mass of metal over the equivalent mass of metal is the same like the mass ratio between mass of oxide and equivalent mass of oxide, and mass of oxygen over equivalent mass of oxygen. So in our situation we can calculate mass of oxygen, which required in our reaction. It's a difference between mass of all oxide and mass of metal. So 3.315 grams minus 2 equal 1.315 grams. And now we can easily calculate equivalent mass from law of equivalence. And in this situation, equivalent mass for metal, it's a mass of metal multiplied equivalent mass for oxygen and divide on the mass of oxygen. So we have 2 multiplied 8 divide on
1.315, and it gives us 12.16 grams. Now we need to determine which metal we have. We can do it through atomic mass. You remember that for pure element or for simple substance, equivalent mass is a ratio between atomic mass and valency. So in this situation, atomic mass of metal, it's a product of equivalent mass of metal and its valency. So 12.16 multiplied 2, we have 24.32 grams. And if we take periodic table, we can see that this metal atomic mass, and this metal is magnesium. So in our situation, our metal is magnesium. Next task. To dissolve 16.86 grams of metal, it requires mass of sulfur acid equal 14.7 grams. We need to calculate equivalent mass for metal and volume of gas which released in this reaction. As well, we use law of equivalence, its second mathematical equation. So mass of metal over equivalent mass of metal is the same ratio between mass of acid and equivalent mass for this acid, H2SO4. But of course we need to calculate volume of gas that's released in our reaction, and according to reaction between metal and acid, we have hydrogen in this case, but for hydrogen, as you remember, it's better to use volumes. So in this situation, volume of hydrogen over volume, equivalent volume of this gas, the same ratio like between masses and equivalent mass for metal and acid. But to calculate equivalent mass and volume of hydrogen, we need firstly to calculate equivalent mass for acid, and from theoretical part you remember that for acid it will be molar mass of acid over numbers of hydrogen cations in this acid. So in this calculation we have a molar mass of acid 98 grams, and in this situation we have just two cations of sulfur acid, two cations of hydrogen, and in this situation it equals 49 grams. So equivalent mass for metal it's a mass of metal multiplied equivalent mass of acid and over mass of acid. And here mass of metal 16.86 grams, equivalent mass for metal for acid 49 grams, and mass of acid 14.7. And in our calculation we have 56.2 grams. And as well we need to calculate volume of hydrogen. We can use, of course, this mathematical equation, but you remember that this ratio gives us numbers of equivalents, ratio between hydrogen volume in our reaction and equivalent volume of hydrogen. And this ratio already calculated, and it equal 0.3 mole equivalent. So volume of hydrogen in our reaction, it's a numbers of equivalence multiplied equivalent volume for hydrogen, and it equal 0.3 multiplied, you already know equivalent mass for hydrogen in previous calculations, so it equal 3.36 liters. Okay, now we have reaction between metal and acid. We have three different metals: aluminium, calcium and magnesium, and all these reactions give us the same quantity of hydrogen. Let's consider that it produces just one equivalent of hydrogen. And we need to determine mass of which metal is required less. So we have three metals: aluminium, calcium and magnesium. We know that numbers of equivalents for hydrogen in reaction for acid and for all metals are the same. Numbers of equivalents for metal, the same like numbers of equivalents for hydrogen, equal 1 mole equivalent. So mass of metal, it's a number of equivalents for this metal multiplied equivalent mass for this metal. You remember metal is a simple substance, so we can calculate equivalent mass for pure metal like ratio between atomic mass of this metal and valency of this metal. So in this situation, mass of aluminium 1 multiplied atomic mass of aluminium 27, valency is 3, so it gives us 9 grams. Mass of calcium 1 equivalent of calcium multiplied atomic mass of calcium 40, valency of calcium is 2, so we have 20 grams. And for magnesium, the same situation, 1 equivalent, atomic mass for magnesium 24, valency 2 as well, so we have 12 grams. And we see that in our situation, task of this reaction, of this calculation to determine mass of which metal required less, so in our situation is aluminium. In the next task we have molar concentration of magnesium hydroxide, and it equal 0.2. Our task to calculate normal concentration of this solution. To determine normal concentration, first of all, we need to remind what does it mean, molar concentration and normal concentration. Molar concentration is the numbers of moles for pure substance in 1 liter of all solution. But normal concentration, it's a numbers of equivalents for the same substance in 1 liter of this solution. So actually we need to calculate numbers of equivalents for magnesium hydroxide. We know that to calculate it, we need to know mass of this substance and equivalent mass of this substance. Equivalent mass for magnesium hydroxide we can calculate from molar mass of this substance and numbers of hydroxyl groups. In our situation, molar mass of this substance equal 58 grams, and you see that we have 2 hydroxyl groups, so equivalent mass in this situation, 29 gram or 1 mole equivalent. Okay, where we get mass in this situation? Mass we can calculate from molar concentration. As I already said, molar concentration is the numbers of moles for pure substance in 1 liter of all solution, so we can say that we have 0.2 moles. So, mass of this substance, the numbers of equivalents multiplied molar mass, and what we have, 0.2 multiplied 58, so it gives us 11.6 grams. And now we place such numbers in our equation and numbers of equivalence. In this situation, 11.6 over 29, and it gives us 0.4 equivalents. So we can say that normal concentration for this substance is 0.4 mole equivalents in 1 liter of all solution. But this is a long way. We can calculate it a bit shorter. As you remember, numbers of equivalents, it's a ratio between mass and equivalent mass. Let's place formulas for equivalent mass and mass exactly in this formula. What we have? Mass, it's a number of moles multiplied molar mass, and equivalent mass, molar mass over numbers of hydroxyl group. And what we can do, we can cross this molar mass, and in our situation we have number of equivalents, it's a product between numbers of moles and numbers of hydroxyl groups. So we just, to calculate normal concentration, we just can multiply molar concentration on numbers of moles on numbers of hydroxyl groups. So multiply 2 and it gives us 0.4 mole equivalents. And the same situation, normal concentration for this solution, exactly this solution, this molar concentration, 0.4 mole equivalents in 1 liter. So you see that differences between normal concentration and molar concentration, equivalent mass and molar mass, just because we have 2 hydroxyl groups in our substance. In this task we as well need to calculate normal concentration, but when we use titration. In chemistry, to analyze different substances, different solutions, we use titration, and exactly titration when we have neutralization reaction between acid and alkali, and we determine concentration of one substance, of one solution, using solution with non-concentration. We add small portions of substance with non-concentration, and we reach equivalent point, need to determine equivalent point where acid and alkali react in equivalence proportion. So in our situation, we have 25 milliliters of acetic acid, and for this titration we use 20.5 milliliters of sodium hydroxide, and we know concentration, normal concentration of this hydroxide. It equals 0.1146 0.145 mole equivalents in 1 liter. So, our task to calculate normal concentration of acid. According to third mathematical equation of law of equivalence, you remember that product between normal concentration for acid and volume of this solution, the same as a product of normal concentration for sodium hydroxide and volume of sodium hydroxide. And in this situation, normal concentration for acid is the ratio between normal concentration for sodium hydroxide, volume of sodium hydroxide, and volume of acid. So in our situation, normal concentration 0.145 multiplied volume of sodium hydroxide 20.5 and volume of acid 25 milliliters. So in our situation, normal concentration for acid 0.09 mole equivalent in 1 liter of all solution.